13.2. Today we're starting exponential growth and decay functions. I can tell you that exponential growth is very similar to geometric growth. They're exactly the same, actually, okay? Exponential growth is something that grows very, very quickly. You've probably heard on TV, man, it grew exponentially, right? They're using it as an adverb to describe how fast it's growing. And they really mean, when they say exponentially growing, they mean fast, okay? So things that grow exponentially do grow very, very quickly. Here's kind of what makes them exponent. You have a variable, let me use red here, I guess. You have a variable exponent. You have a variable in the exponent, and you have a numeric base. Okay, that's what makes it exponential. Here's an example of some of them. Y equals 2 to the power of x. Y equals 1/3 to the x power. Those are examples of exponential functions. They have a number that's a base, and they have a power that's a variable. Okay, so notice how that's different. These are not exponential. Y equals x squared. That's not exponential, is it? That's flipped around. That has a number exponent and a variable base. That is not, okay? So they have a variable exponent and a numeric base. There are some qualifications on the base, though. Not all numbers work. The base has to be positive, and it can't equal 1. The reason it can't equal 1 is because 1 to any power is 1. 1 to the first is 1, 1 squared is 1, 1 cubed is 1, 1 to the 100th power is 1. So 1 doesn't work. But the base has to be positive. And there's two different ways the base can be. If the base is greater than 1, we say that it's exponential growth, and it looks like that. So like 2 to the x, as I did up above, that's exponential growth. Y'all have heard of cell division, right? Mitosis, meiosis. Cell division, y'all haven't heard of mitosis? Cell division? One haploid cell splits into 2, 2 split into 4, 4 split into 8. That is 2 to the x power. Those cells grow very, very rapidly. Okay, that's exponential growth. Anytime the base is bigger than 1, it's going to grow. There is a y-intercept here of 0, 1. We'll call that the y-intercept, because anything to the 0 power, remember, is 1. 2 to the 0 is 1. 5 to the 0 is 1. 10 to the 0 is 1. So that's your y-intercept. And then there also is another feature here on the x-axis. This is called a horizontal asymptote. The horizontal asymptote is like a vertical asymptote, except it's fallen over. So here's what the horizontal asymptote does. As you go out to the left on the graph, like hop on the graph and just head out to the left like it's a slide, you're going to get closer and closer and closer and closer and closer to the x-axis, but you're never actually going to touch it. You can go out forever to the left-hand side, and you will still be just a tiny hair above the x-axis, okay? We call that a horizontal asymptote. Now, it only affects the graph on the left-hand side. As you go out to the right, you're going up to infinity, okay? So on the left, you're going down to 0, and on the right, you're going up to infinity. So if we talked about the end behaviors of the graph, which we could, the left end behavior is 0, and the right end behavior is infinity. There's your parent function for anything of the form b to the x, where b is greater than 1. Okay, that's exponential growth. Now, if the base is between 0 and 1, like 1/2, what happens if you keep taking powers of a half? A half, a fourth, an eighth, a 16th, a 32nd, a 64. They're getting what? They're getting smaller. So now this is exponential decay. Decay means decrease. If decay creeps you out, it's exponential decrease. Okay, but they both start with D. They're getting smaller. This one still passes through the point 0, 1, and it still has a horizontal asymptote at y equals 0, the x-axis. Okay, but the behavior is flipped around. Now as we go out to the right, we're going down to 0, and as we go out to the left, we're going up to infinity on the left-hand side. Okay, exponential decay, exponential decrease. Have y'all heard of radioactivity? Yeah, like in Chernobyl. When radioactive elements, isotopes, are released into the atmosphere, they start to decay exponentially. And we measured how long it takes them to get smaller by calling them half-lives. Have you heard of half-lives? Like carbon-14 roughly has a half-life of about 5,700 years. So every 5,700 years, carbon-14 loses half of its mass, half of its mass, half of its mass, okay? That's exponential decay. It gets smaller and smaller. But there will always be some carbon-14 left in it because it never reaches zero. There's a horizontal asymptote there. And that's why they can find these fossils that are infinitely years old. They can still find trace amounts of carbon-14, and they can compare it to stable carbon-12, and they can determine basically how old that artifact is. It's pretty cool, carbon-14 dating. All right, let's look at these features now from the exponential growth and decay. Let's jump back to the left column, okay? Left column, yum. As the value of x increases, the value of f of x goes what for growth? As the value of x increases, the value of f of x also increases, right? It increases, I'm going to add this, it increases to infinity. See that? It increases to infinity. What's the reference point? It's the point 0, which is the y-intercept. What's the asymptote? It's y equals 0, which is also known as the x-axis. What's the domain? Oh, that's a good question. What values of x does this graph take on? 0 to infinity? That would be from the y-intercept to the right? Negative infinity to positive infinity. What's another way to say that? Double bar R, right? All real numbers. All real numbers. Okay? What's the range of this graph? What y values does it take on? 0 to infinity. Good. So we're going to write that as an interval. Y epsilon, 0 to infinity. Infinity always gets a parenthesis, right? What does 0 get here? A bracket or a parenthesis? Bracket means we reach 0. Do we ever reach 0? I told you the asymptote prevents us from actually reaching 0. So it's an open interval. Or you could just say the set of all y such that y is strictly greater than 0. Either one of those. Okay, that's for exponential growth. All right, exponential decay. As the value of x increases, the value of x does what? Decreases, and I'm going to add this, it decreases to 0. What's the reference point? It's still 0, 1, which is still the y-intercept. What's the asymptote? It's still y equals 0, which is still the x-axis, but it only affects the graph on the right-hand side. You got to keep that in mind. The horizontal asymptote, we draw it all the way across from left to right, but it really only affects the graph on one side. What's the domain? All real numbers. And what's the range? Is the range different from growth? It's exactly the same. So what's the only difference between the two? The top line, isn't it? The top line is the only difference between the two. Everything else between them is the same. One, the base is bigger than 1 and it grows exponentially. One of them, the base is between 0 and 1 and decays exponentially, or decreases. I don't care if you say decay or decrease. We typically say decay. All right, so now we can start transforming these puppies, right? Because the basic parent functions are going to be too boring. So we have the same old A, B, C, and D, okay? A is your vertical dilation factor. If it's bigger than 1, it stretches. If it's between 0 and 1, it compresses. And if it's negative, it reflects across the x-axis. Same old, same old. Your B is your base, so we don't talk about a horizontal dilation. But your C is your horizontal shift. And your D is your important one. It's actually the more important one. This is your vertical shift. And what important feature on this graph is going to move when we shift these graphs up and down? The reference point will move for sure, and we can maybe follow it. But what other big, huge feature? The asymptote will move. Now, here's what's cool about the D value. Your asymptote starts at y equals 0, doesn't it? On the x-axis. So if we move the entire graph up 3 units, guess where your new asymptote is? 3. So we're going to have a HA. Are you okay with me abbreviating horizontal asymptote HA? Ha! Thank you. So we have a horizontal asymptote at y equals D. That's going to be the location of your horizontal asymptote. And when you draw these things, you want to draw this first, because it's a literal guideline for your graph. If you have your horizontal asymptote drawn, then you know that you could draw the graph on one end approaching it, okay? A does two things. It dilates vertically, so it stretches and compresses vertically. If it's negative, it also reflects across the x-axis, which means it lives below the horizontal asymptote. C is your horizontal shift, and D is your location of your new ha. Okay, let's try it out. Example 1. Determine whether the function models an exponential growth or decay, and then describe the transformations from f to g, and then graph it. Identify the reference point and the asymptote for each function. Write the domain and range. Ooh, that's a lot of info, isn't it? Okay. So first of all, the parent function is 4 to the x. Is that exponential growth or decay? First of all, is it exponential? It's not. 4 to the x is not exponential? It is, right? We have a variable in the exponent, and we have a numeric base. And because the base is 4 and it's greater than 1, this is exponential growth. Yeah. Times 4 times 4 times 4 times 4. That's going to get bigger pretty quickly. All right, let's look at g of x. Is g of x in standard transformation form? It is. So let's list the transformations from left to right. What is the 2 going to do to this graph and any graph? Vertical stretch by a factor of 2. Same as it would do for any other function. All right, what does the plus 3 do? Left 3. We'll just put L3. And then what does the plus 5 do? Up 5. Now, I'm going to put U5, and then in parentheses, I'm going to put ha at y equals 5. We know right away that there's a horizontal asymptote at y equals 5. All right, it says exponential growth or decay, circle one. Okay, I'll circle exponential growth. Transformation, we just did that up here. I'm going to move it down. Good thing we have notability. Notability. All right, what's the reference point on f of x, the original untransformed function? Where is it by default? 0, 1. 0, 1, right? That's your default. What's your asymptote by default? Y equals 0. I don't know why. Yeah, it says f of x. So we're talking about the original function. All right, now, are you ready to move these dudes? Let's move them over. What happens to the reference point? Well, let's do these one at a time, like we did back in the day. What happens to the graph horizontally? What happens to the 0? It moves left 3. So where's the new x value? Negative 3. Okay, comma. Now we look at the y value. What happens to the y value? We do two things to the y value. We double it, and then we add 5 to it. We double it, and then we add 5 to it. So we have to do it in that order. What's 2 times 1? 2. What's 2 plus 5? 7. Guess where your new reference point went? 3, negative 7. We've done that before, right? Just with different functions. The horizontal piece takes care of the x, and the vertical piece takes care of the y. All right, what happened to the asymptote? We already did that. It's at y equals 5. Y equals 5. All right, now for the domain, what's the domain of G? That's the transform graph. Guess what you could do with your eyes closed for the domain every time? All real numbers, double R, R. Oh, yeah. Now, if it asks for an interval notation, you could say y epsilon, negative infinity to infinity. If it asks for a set notation, you could say the set of all x such that x is an element of the real number, something like that. Okay, now, for the range, bless you. For the range, you're going to want to get the range from graphing it. You don't want to guess the range. So let's graph it next. What's the first thing that we should probably plot? The asymptote. So I come with the 5. 1, 2, 3, 4, 5. There's y equals 5. I'll mark it. And then I'm going to come in here and draw a line. Okay. The next question is, did we reflect it across the x-axis? Because if we did, that would be reflecting across the asymptote and it would live below. Did we reflect it? No. So it lives above. What's the next thing we should probably plot? This is number 1. The next thing we should probably plot is number 2, the reference point, negative 3, 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. There's your reference point. Okay, now all we got to do is draw a graph through that point. That's what? Growth or decay? Growth. So we're going to come from the horizontal asymptote. We're going to come from the left, and we're going to pass through that point, and then we're just going to take off, getting bigger and bigger. We actually go right off the graph, don't we? And then we'll label it as g of x. That's all we got to do. Fun easy, right? Fun easy. All right, now we can get the range. What's the range of this graph? Does it live everywhere greater than 0? The range is always going to come down to the horizontal asymptote. It's either going to be above the horizontal asymptote or below the horizontal asymptote. 5 to infinity. So y epsilon parentheses 5 to infinity, which is above the asymptote. The range is always either everything greater than the asymptote if it lives above, or everything less than the asymptote if it lives below. Always. Unless we're restricting it over a certain domain. All right, there we go. That was example 1. Comments or questions on example 1? Y'all could do this on your own. I know you can. This is honors algebra 2, for Pete's sake. Who's Pete? Example 2, write the function based on the transformation given. Oh man, we've done this 1,000 times with other functions. Let's do it with the new exponential. The function f of x equals 0.3 is transformed right 2 and up 7. First of all, is 0.3 to the x power, is that growth or decay? It's decay. Very good. It's decay because the base is between 0 and 1. Now, if I'm going to write the new function g of x, that's the transform version, if we're moving right 2 and up 7, is there an a value in front? No, it's just 0.3 to the, and now right 2 is going to be x what? Plus or minus 2? Minus 2. Make sure you write it small and in the exponent. The inside of the exponential is in the exponent. So make sure that that is written small or smaller and up. It's written smaller and up. Okay, it's part of the exponent. And then the up 7 is going to be back on the ground floor, up 7, right? This is bigger on the ground floor. Bigger and on the ground floor. And there you go. Fantastic. What's the range of this function, g of x? Do y'all know what the range of this function is without graphing it? Very good. Yeah, 7 to infinity. Everything's strictly greater than 7. Because we moved it up 7 and we didn't reflect it across. The only thing that's going to make it below the horizontal asymptote is if a is negative. Then it'll reflect across and you'll have everything below the asymptote. But yeah, if you know the asymptote's at y equals 7, the range is everything bigger than 7. Piece of cake. Easy. All right, let's look at example B. The function f of x equals 5 to the x. Is that growth or decay? That's growth. Exponential growth, e.g. Okay? Is reflected across the x-axis and then translated left 3 units. Okay, so g of x is going to be the following. How do I reflect it across the x-axis? What do I put in the front? A negative. So that becomes negative 5 to the x, and then we're translating it left 3, so is it x plus 3 or minus 3? Plus 3. It's still the opposite of what it looks like, right? And we write it smaller and up there with the x plus 3. And that's it, right? That's it. Can anyone figure out the range of this function? Close. Not 0 to negative infinity, but least to greatest, negative infinity to 0. Yeah, negative infinity to 0. Negative infinity to 0. Everything less than 0. Sweet. Letter C. The function f of x equals a half to the x. Is 1/2 to the x growth or decay? Exponential decay. It's ed. Yeah, that's right. It's vertically stretched by a factor of 2 and translated down 4 units. Okay, so here's what g of x is going to be. Vertically stretched by a factor of 2. A 2 goes into the front times 1/2 to the x. And then what is the down 4? Is it in the exponent or on the ground floor? Ground floor. And it's minus 4. Yes, yes? Yes, yes. What's the range of this function? Negative 4 to positive infinity. Excellent. We didn't flip it across the x-axis, so it's everything above the horizontal asymptote, and the horizontal asymptote is at negative 4. Very good. Keep your phones away. All right. Comments so far? That's example 2. Man, we're rolling through this section. There's only one more example left. I don't even know if I need to do it with you because, well, I will. Write the exponential function that will model the graph shown at the right using the specific value of the base. Identify the domain and range of the function. Okay, all right. So the base is 2, so it's got to be exponential growth. So here's what we're going to start with. We're going to start with the form f of x equals a times 2 to the x minus c plus d. You know what I think we should even start with? I don't even think I'm going to do a horizontal shift. I think I'm going to let the horizontal shift be taken up by the a value. Let's see if this will work. Because the horizontal shift is going to be hard to visualize, but the vertical shift is not. So let's start with this. Let's take c out of it. I plugged my base in. I took c out of the equation. I've got a and d. Okay, now, the first thing that you want to do is get the d value. Get d value from the graph. Yeah, we come down here and we see it's what? -1. There's a horizontal asymptote, an HA at y equals -1. So I'm going to plug that in. So here's what I have now. So I have f of x equals a times 2 to the x minus 1. Okay, so now guess what I'm going to do? I'm going to use a point. I'm wondering if they're intending one of those points to be the old reference point. It's kind of hard to tell. Which of those points would you prefer to use? 3 and 3. Okay, so let's use it. I'm going to say at the point 3, 3. And then I plug in. So this is my f of x and this is my x. So I get 3 equals a times 2 to the third minus 1. And solve for a. All right, so let's solve for a. What's another name for 2 cubed? 8. So I get 8 times a, which is 8a minus 1. Add 1 to both sides, you get 4 equals 8a. Divide through by 8, you get 4 eighths, which is a half. Okay? And then step 3, all you got to do is plug in your a value. So that's what we're going to do. We're going to plug it right back into right here. So we get f of x is equal to 1/2. I'm going to put in parentheses times 2 to the x minus 1. Does it matter which of those 2 points we use? No, it shouldn't. Shouldn't matter. Now you could verify it. Let's see if we get the other point. Okay? The other point says when I plug in a 4 for x, I should get out a 7 for y, right? Let's try it into our new equation. What do I get when I do f of 4? Let's just see what f of 4 is. It's 1/2 times 2 to the 4th minus 1. Well, that's 1/2 times 2 to the 4th is 16. 16 times a half is 8. 8 minus 1 is 7. Did it work? It worked. Okay, cool. So this is the form that you want to start with. You want to start with your base and then take c out of the mix. It's very hard to get a c value unless you're told that it's shifted horizontally. But the d value is easy to get. Okay, what's the domain? I'm going to do it with my eyes closed. What's the domain? All real numbers. I did it with my eyes closed. Did it fit? No, I better not do it with my eyes closed. I better fit it in there. All real numbers. And the range, you can get the range easily from the graph, right? It's the set of all y such that y is strictly greater than -1. Or you could say y epsilon -1 parenthesis to infinity, either one. All right, so let's review what we did here on this last question because it's important. We do this in every section when we have a new type of function. We start with our template, which is a times b to the x plus d. We take out the c. It's too hard with the c. We plug in the given base, and that gives us the purple box answer. Then we get the D from the graph and we plug it in, and that gives us this version in the box. And then we pick either one of the points from the graph and plug it in for x and f of x. We find A, and then we plug A back into that same form, and that gives us our final answer. And if you want to check the other point, you can. All right? So three-step process. Original form with the base, plug in your D value from the horizontal asymptote, pick a point, plug it in, solve for A, and then rewrite it. Got it? And then here's your template. If you do that on the homework and you need an example, you refer back to this right here. Okay. And that's the whole section. We finished it early. You have the rest of the period to work on this. It's due Thursday, but maybe you can get it done today already. Who knows? No, that was just 13.2. We'll do 13.3 tomorrow. Yeah, and 13.3 tomorrow is going to be easy. We're just picking a particular base. I'll introduce you to the number E. What did I say? The number E? Yeah, I'll introduce you to the number E. It's the most important number in all of analysis. It's almost as important as the number pi. Okay, any comments or questions? All right, have a good rest of the time. It's back to you.